Thank you, Norbert, for the nice introduction. And I also like to thank the organizers for inviting me here, especially Alexandra and Joseph. It's really my great pleasure, and I feel very fortunate to be given the opportunity to present my work here. So just a little bit warning. Well, my talk, you will not see any tensor networks. So I'm a mathematician at Duke University / quantum information scientist or quantum computing scientist. So this is going to be a pure quantum talk, if you like. So you will unfortunately not see tensor networks. But what I plan to do is that I will introduce these two very important problems in quantum information science that many people have been working on. And I think maybe I can give you an overview of these problems, sort of the state of art of these two different problems, and I will highlight one work of mine on each of this side, and maybe you can sort of view this as an invitation to study this problem using advanced tensor network tools that for these interesting problems. All right, so let's get started. I think I'm very fortunate to be in this afternoon because this morning Elisa already gave a very good motivation of why we want to do a quantum quantum dynamic simulation. So in our community, we also call this problem Hamiltonian simulation. It just means that I have a dynamics that is governed by a Hamiltonian, where we want to simulate the dynamics. The setup is very simple. We can have some Hamiltonian, where this morning you have also seen that Hamiltonian can be time dependent and so on and so forth. But for simplicity of my talk today, I will just simplify it to look at time independent Hamiltonian. Mathematically speaking, this problem is just really simple. We can certainly write down this differential equation. This is nothing but the Schrödinger equation that we are all familiar with. And then the exact solution is really nothing but this matrix exponential acting on the state that we begin with. And then you can sort of translate this Hamiltonian simulation problem into I want to come up with approximate unitary, and then acting on my initial solution and initial condition, and I want to make sure the error is somehow bounded by a procedure of your choice. Well, you can think that how do you implement this approximation of the unitary? You can imagine if you implement it, say, in a tensor network way, there is a classical algorithm, or if you implement it as a quantum circuit, and then you get a quantum algorithm. So for the rest of my talk, I will mainly focus on quantum algorithm, but similar bounds actually also holds classically. All right, so basically we want to estimate these quantities. We want to design algorithm and make sure that we have certain error guarantee. That's called the error to be procedure. One immediate estimate that you can immediately make the inequality is that you can drop the initial condition. Instead of looking at the vector norms of these solutions, you can instead look at the operator norms. This is just a simple fact coming from all of the wave functions IL2 normalized. So this is as simple as that. Hence, people in the community has been focusing on this particular error metric, which is the operator norm between the approximate unitary of your which is specific according to the algorithm that you are using, and then corresponding to the exact one. The error metric is this.
So in practice, the U app is chosen independent of psi naught anyways?
Yeah.
So this is completely reasonable to study then?
Yeah, that's right. That's right. That's part of what I'm going to discuss here. So the nice thing, what I'm trying to say here is that this is really the worst case scenario error estimate, if you like. If you were able to make this hold true, then it will automatically work for arbitrary initial conditions that are given in a particular problem. Well, now you may think that how, say, in the worst case scenario, how difficult is this problem? So we know that Hamiltonian simulation is a BQP hard problems, which essentially suggests strongly that there should not exist, for the worst case, for example, should not exist a polynomial classical algorithm to do the similar task. Well, now this is a really well-studied problem. I should at least say that this serves as the original motivation to build a quantum computer and remains as one of the most basic fundamental problems in quantum computing. And you may wonder, what is the challenge here? Well, I really want to say that one challenge, obviously, is that as the operator norm of H increases, this will the unitary is sort of wrapping around, and this really determines the speed of the oscillation behaviors. So as h increases, the high oscillation you will have, it's natural to imagine it will cost you more to simulate this dynamics.
Wouldn't you expect that at some point it gets easier again? Because if you go for a certain time and it oscillates a lot of times in that time,
yeah, you can average. You
can do this all the time in quantum optics or so, right?
Yeah, that's right. That's possible. That's possible. You may expect a long time and say normalize or average out behavior. That's very likely. So, yeah,
so
that's right.
Are you going to be allowing arbitrary Hamiltonians or picking from a special class of Hamiltonians?
Yeah, I will. In my work, I will discuss a particular class, and you will see the particular class that I work with. This is a general introduction of what people typically do. Yeah, thank you very much for the question. Any other question before I continue? All right, now I'm just going to summarize a number of existing techniques, primarily in quantum. However, totalization, I would like to emphasize, this is really a technique that is used everywhere. It doesn't matter you want a quantum implementation or classically. This is really one of the most ancient way of doing Hamiltonian simulation, remains one of the most, say, studied and popular way up to now. This totalization actually was so well studied and celebrated in different fields to the level it really has different names. So in case if you are searching the literature, you will find that sometimes people call it totalization or Total Suzuki. Typically, physicists like to call it this way, and I also like to call it this way personally. And if you talk to computer scientists, sometimes people call them product formula. Well, they mean the same thing. And mathematicians, sometimes they either call them time splitting or operator splitting. There are vast literature on these problems, but nevertheless, it really means the same thing. So I'm just going to illustrate the idea using a very simple Hamiltonian. Suppose I can written as a sum of Laplace, sum of two terms. You can imagine, for example, a general say n-body Hamiltonian can be written as a linear combination of n-body polys, or maybe you have your favorite system, say transverse and Ising models, and then you can written as a sum of the two terms and so on and so forth. So if you are in this particular form, and on top of that, let's just focus on time-independent case, what Trotter is saying that you are going to chop your time interval from 0 to capital letter T, that is where you want to simulating, into a number of small time steps. And the number of time steps, I'm going to call them L. And on each of the small time steps, you just apply either H1 or H2 in alternatively. This is certainly an approximation which comes with an approximation error, and it's not surprise at all that this error should be should be upper bounded by some operator norm regard the Hamiltonian, because you are approximating two operators, so they should be upper bounded by a Hamiltonian. Furthermore, it's actually not. Please.
If H1 and H2 commute, this is exact?
Then it's 0. Yeah, so it's what I want to emphasize, this is actually a very elegant three-line proof. You don't have to do any like Taylor expansions. You can write exact error formulas to easily show this is true. In the sense that you not only just have an operator norm, the operator norm is actually regarding the commutator. Just imagine as the intuition you pointed out, imagine H1, H2 actually commute with each other. Then this, we know that from linear algebra, this formula become exact. So Trotter is so special, it's so nice, so that you really have this commutator scaling. This is a very important thing that was find very useful applications in quantum simulations in this particular paper at PRX. And now I'm going to say about other quantum simulation techniques as a quantum algorithm for Hamiltonian simulation. I'm going to group all of the other algorithms who are not a product formula. I'm going to call them the post-Trotter algorithm. It's just not me inventing these names. People also call post-Trotter in our community. This includes the more familiar, if you are coming from quantum community, the QSVT, quantum signal processing, qubitization, and so on and so forth. The point is that all of these problems will give you a cost that is polynomial dependence on the operator norm of H. It's not a commutator scaling. It gives you operator norm dependence of the H itself. And what is the takeaway here? Well, I sort of want to say that, sort of recall echo the original point that I was trying to make. As operator norm of H increases, the error bound really increases, which we have already seen, so that as H norm become larger and larger, you do face a increased difficulties in terms of a cost in the simulation, which I has already demonstrated discussing all the existing techniques.
So it's just, I mean, before there was a commutator, and I said, now you get something which depends like a poly on the norm of H.
Yeah. But
certainly if it's some kind of spatially local Hamiltonian, I mean, the commutator goes like system size squared, right? So
yeah, yeah.
Kind of, I'm not sure, is
that better or worse? So that's a perfect
happen?
question. So if you look at, say, first order torter, you do not use the commutator bound, then naively what you will get is operator norm squared. So for transverse Ising model, for example, you will get n squared, versus you play around with the commutator, you get linear in n. So that is a polynomial in system size gaining that you can play around using commutator scaling. That's one example. Another example is more relevant to sometimes what I do, so-called unbounded Hamiltonian simulation, which are basically we look at the Hamiltonians in the first quantization setting, where you have differential operators coming from the momentum. If we look at momentum from L2 to L2, momentum differential operators are unbounded because it maps HS to HS minus 1. So if you naively apply, say, the operator norm, you get infinity. However, if you think about your Hamiltonian, well, that's not going to be the Hamiltonian you would like to think. But if imagine you have the Hamiltonian as simple as momentum plus position operator, you look at the whole operator norm, it's going to give you infinity. However, you look at the commutator, it's just 1. It's h bar. So it's a finite constant. That's why commutator scaling is actually very good in terms of, I will recall this point later. All right. So a very, very natural question is really that can we weaken the operator norm's dependence of H? Well, we can make it into a Nasse commutator already give you a dramatical improvements in many cases, but still it is operator norm dependence. Well, you may wonder, like, why should I even care about the operator norm dependence? Isn't that for a given Hamiltonian of my choice that I'm interested in, it's just going to be some, say, fixed constant? Well, it's a given problem, and I just calculate the norm, what's the big deal? Well, you immediately should realize, well, here is just some figures to entertain my audience. In the same language of, say, k-local Hamiltonians, then it's associated with the system size, where this system size is the number of qubits that I refer to, the whole system size is 2, well, the matrix size correspondingly is 2 to the n. So this is the system size that I was referring to. And also, if you think about the unbounded Hamiltonian cases in the first quantization particularly, that was the example I was trying to give. Because Laplace is an unbounded operator from L2 to L2, it's actually unbounded, it's infinity. The issue is that even if you try to discretize it, it do not solve the problem. But I will not really cover this particular part. I do have another recording regarding this issue. Maybe you can find me talking about particularly how to deal with this case, either in my in KITP or IPAM that I have a specific recording, or you can talk with me afterwards. And a third case is I will address a little bit in my talk is today is there can be some natural scale separation in our problem, particularly if we think about molecular dynamics, these nuclei, because electron and nuclei, the scale really is not the same. So there is some natural scale separation of the problem, which you can identify as some small parameter, and your Hamiltonian turns out will be inverse dependent on this very small parameters. So all of these cases, what I want to trying to say is that operator norm of H is not just a constant that you should never worry about. It is something one should really think about. So now I'm going to talk about a little bit more how do we weaken the operator norm dependence of H. If you think about it carefully, if you want to get rid of something or maybe relax it a little bit, you'd better know where does operator norm of H come into the cost estimate, right? You have a complexity estimate, where does H enters into the game? It turns out you look at all of the existing quantum algorithm, operator norm of H will enter into your cost estimate or complexity estimate from 2 different places. Number one is you look at the circuit implementation. Typically, you implement as a quantum circuit. This is a place where you will very likely pay a cost of operator norm. And the other place is error estimate, which I already tried to illustrate you a little bit previously. So out of all of the existing algorithms, why do we say Trotter or product formulas is so special? It turns out this is the unique algorithm. This is the only algorithm, the product formula in general. Doesn't have to be deterministic Trotter. It can be randomized Trotter and so on and so forth. Product formula is so special. It's the only quantum algorithm do not reintroduce this circuit operator norm through the circuit implementation. The high-level idea for my quantum friend is really just because everything is unitary, so you do not need to do a block encoding at any notion of LCU and so on and so forth. That's the reason you do not need to pay an operator norm price. So in this case, then if we only focus on Trotterization, it means that all I need to do in order to weaken this operator norm dependence is do something with the error estimate. Well, I'm a numerical analyst, and this is what we do all the time. So now if you think about where does the operator norm dependence come into the game when we do the error estimate, which was going back to the question from Joseph, it's not surprising at all. It is precisely this error estimate you dropping from the vector norm versus the worst case scenario you are paid in this operator norm dependence. So what I'm trying to say here is really not anything fancy. All that I'm trying to say is that although in terms of complexity, it's very valuable if we study the worst case scenario, however, in a practical situation, maybe specific case error estimate can be more relevant. Specifically for these problems, if you take, say, the special initial condition into account, and then you can, if you can improve the error estimate, then you can get improved estimate of the product formula. But unfortunately, not for the other quantum algorithm, as what I was trying to illustrate here. All right, then you might think that, okay, I can take an initial consideration of the initial condition. Is this only the special structure maybe I can take in the problem? The answer is certainly not. There are a number of different things you can take advantage of. Number one is this initial condition. I just showed that this is definitely a weaker measurements. You can get improvements. The other thing is very natural. If you have an observable that you want to measure in the end, a position observable, momentum observable, so on and so forth, you can look at the Heisenberg picture and try to measure the errors in the Heisenberg picture, which are observable error norms, and you can see very easily this is guaranteed to be a weaker norm compared to the worst case scenario. Well, you think, okay, I have initial condition, I have observable. What if I take both of them special? And then this is our familiar metric. This is nothing but observable expectation. You can certainly take both of the things special and make it the error metric of your choice. Now you may wonder, okay, fine, you present all of these different error metrics of specific and worst case scenario. What are the relationship between all of them? I think a major takeaway maybe of the first part of the talk is really not the technical things that I'm going to present next, but rather this high-level picture is all of these different metrics. You can put them on this number line, where on the right-hand side is more restrictive, on the left-hand side is weaker. So this is either take initial condition into, this is take observables, and this is both. So as you see, the weaker norm you make, the smaller errors you will get, and the better cost estimate you will get in the end of the day. This is sort of the idea. Now, at this point, you can be like, okay, I get it. You have different error metric of our choice, but what's the point? Is there any applications? Okay, you can get maybe a factor of 2, a factor of 10, a constant improvements. That is great, but maybe not that surprising. Can you illustrate in certain examples, in certain Hamiltonians, maybe I can get even, say, asymptotic improvements in certain parameters of our choice. That's precisely what I'm going to discuss. We do have asymptotic improvements using this special specific case estimates for different problems. Unfortunately, I will only dive into one specific easier story task so that it fits in my time slot. And I will not be able to talk about the unbounded situations. And especially superconvergence is actually a totally another story. You can either talk to me or discuss with me about or look at our paper or maybe on my talk recordings. And the second situation I'm going to actually discuss today is this semiclassical situation where we have this scale separation. I'm going to really look at a really sort of toy model, but just sort of illustrating in terms of analysis, estimate what I can do in terms of these specific metric. And then there are also some local Hamiltonians, say K-local Hamiltonians. I will not discuss it in the first part, but you will see it again when I discuss about the Hamiltonian learning card. That will be a K-local Hamiltonian. Just before I move on, I want to emphasize one thing is that there is really no universal treatment to gain improved estimates for these specific cases. Actually, the way to gain improved estimate of all of these three cases, which I have worked on, but they are all different. So the first case is regularity. The second case is a semiclassical property. The third case is really the locality that is playing a crucial role. And the tools to deal with these problems are essentially very different. Okay, so now I'm going to provide a case study. This is a PhD student that I was very fortunate to work with at Berkeley. And I'm just going to give you this very toy model, which is not designed by me. This is a long study problem in numerical analysis. I will just tell you what my new analysis is about. And I'm going to talk about this multi-scale problem. And luckily, Jingmei this morning also mentioned a little bit about multi-scale problem. In general, well, if you think about applied mathematics and people talk a lot about the multi-scale problem, it can be, say, Schrödinger equation, if I take Planck constant goes to 0, I get the dynamical system, which are particle system. And when I take the particle number goes to infinity, I have the statistical mechanics, both my equations was talked about. And then you take Newton number goes to 0, you have fluid dynamics. So the point is a multi-scale problem is everywhere. And the treatment of these problems in terms of error analysis usually share many similarities, which we will see very soon. But in terms of quantum, I'm just going to fix ideas on this particular problem. I'm going to look at the nuclei dynamics, where in the autonomous units, because of the mass of the electron and the mass of the nuclei differs a lot. So you can see that this is actually a very small constant that is applied in front of the momentum operator, if you'd like. So typically, these multi-scale problems, you can identify a small parameter which resembles the scale separations in your particular problems. In our case, we are going to call it H, which is either the semiclassical parameter, so-called, or you can call it a rescale Planck constant for this particular example. The thing is that if you look at this dynamics, you just look at the Schrödinger equation, and you look at for order 1 time, it turns out nothing too much interesting is going on. However, if you look at this dynamics a little bit closer, you will realize that there are much more interesting thing going on by looking at a longer time. So what people typically do is we will rescale the time. Instead of the original t tilde time, I'm going to rescale by this new time. The point is that when the new time is of order 1, the old time is really a lot of longer compared to you're considering essentially a very, I'm trying to zoom in so that order 1 time is actually a very long time. So for our purposes, it can be reasonable if you just think about this H inverse as a indicator of the scale of this problem. Please.
So you assume the Born-Oppenheimer approximation.
Yeah, that's right.
So you just are given a potential.
Yeah, that's right.
Usually when I think about the nuclear dynamics, I'm thinking of the electrons doing things at one energy scale.
That's right.
Nuclei doing things at another energy scale.
Yeah, exactly.
You're just saying, okay, let's take Born-Oppenheimer, and then, but we're going to do, and then usually chemists would just treat the nuclei classically.
I know. Right.
Like, okay, but you're going to do them quantum mechanics.
Yeah. So this is actually a very, so the original motivation of me look at this problem is precisely what you are discussing. Instead of V of x, we should definitely look at HE and x as a parameter, where we have the kinetic part of the electrons and electronic structure problem, essentially. And what has been in an open problem is what I will show you later has been studied. People try to prove bound for on the numerical analysis side, trying to get rid of this small parameter. People are already having difficulty get rid of the small parameter for this very simple model. Of course, now I can do it. The next natural question would be, I have the full model, and what is the best shelter bound for that? That's precisely what we want to do next. Thank you so much for the question. Any other question before I move on? All right. So this is the so-called semiclassical Schrödinger equation, which was, again, not invented by myself. It can be actually derived from the first, as was said, you take the Born-Oppenheimer, and then you look at the potential energy surfaces and the corresponding dynamics. You can derive on a rigorous level. These are some mathematical references for precisely how people derive it. Also in different it can also arise in different applications, but the point is that this is the equation that I want to work on. So the point is, here is really just a Hamiltonian simulation problem. The real question here, well, it's not difficult to come up with a algorithm to simulate it or a error bounds to do it, but the the key question here is really how does the complexity or the cost depend on on this small parameter h. It turns out if you look at all of the existing algorithm, or before that, maybe let me just show you a numerical demonstration of what this dynamic physical value. It shake a little bit, and you have lots of oscillation. The x-axis is the just one dimension x-axis, just for demonstration purposes. And here is another example of this is roughly speaking what the behavior of the solution will sort of look like. And the point of this discussion is really that this is an unbounded problem which has infinite Hilbert dimension. You definitely need to fix the Hilbert dimension, make it finite. You can choose your Fourier types of orbitals, or maybe you can choose your plane wave basis, or you can choose a grid mesh. However you do it, the point is that the spatial degree of freedom needs to be as small as h, because that's what the oscillation scale is about. And you need to pay this to do like this size in order to resolve all of these oscillations I was trying to show in this. But the point is, after you do that, you really fix this problem of the right-hand side. You fix the Hilbert space dimension, and then you can easily evaluate the corresponding operator norms. It's not surprising at all. The cost is actually all dependent on polynomial of this H inverse parameter, because all of these Hamiltonians are actually H inverse, and it's an easy calculation to check, so are all of these nested commutators. So just to fix the idea concretely, if you look at the first order totalization, what you will get is that error in the solution, actually error in the solution is already a weight curve metric comparing to the worst case scenario, which is the operator norm of the unitaries. But even if you take into account the solution in mind, you still have a H inverse on the right-hand side. This essentially suggests that if H decreases, and you need to increase the number of total steps, you need to increase L in order to get the same amount of accuracy. This is what you can do. However, in numerical analysis, well, why people still study it in numerical analysis is because it turns out since 2002, people find this very nice numerical evidence. And what they see was that for certain observables, a position observable, momentum observable, for certain observables, when you decrease H, it turns out you fix the number of total steps, it still looks pretty good. It matches the numerically at least what is going on. You do not need to increase the number of total steps, which is sort of very interesting and sort of exciting observation at the time. And there were actually 2 reviews dedicated to precisely different error bounds of this problem on Actica Numerica in this particular papers. There exists some heuristic arguments asymptotically. I will show you a little bit later. There is also existing results really focus on error estimates of existing results only happen when we have spatial degrees freedoms all continuous, namely you do not discretize. Well, discretize will cause dramatic trouble in these particular problems, it turns out. I will illustrate what is going on. So the open question here in the numerical analysis community is really that can I provide a rigorous error bounds that you can show that this, in terms of the observables, the right-hand side is really uniform in terms of H, is independent of H, because that is what has been observed in literature. And importantly, you need to account the spatial discretization, please.
Okay, so if I was thinking about simulating this sort of problem, I would think of trying to separate out the classical motion from whatever oscillatory behavior it was. And sort of, I would say Trotter, it sounds crazy because I've got these 2 time scales and anything like that is so. But is it there's nothing known that will really separate these sort of the classical motion?
Actually, I will show you that Trotter is actually already pretty good at capturing the behavior, because I will show you in the next slide. If you take H goes to 0, it turns out Trotter captures the limiting behaviors of, it's precisely a good scale separation problem. That's why for Trotter, there's a hope to get rid of this H on the right-hand side. That's precisely the point. Thank you very much. And so this is our work. This is a sort of informal description of our work. But the point is that we do not have restrictions of the initial condition. You can take arbitrary initial condition you like. And this simple class observable, which means that if you have a torus periodic boundary condition in arbitrary dimension, then you can take observables that is C infinity, which means they are smooth and they can be differentiable of arbitrary orders. And if you look at Rn, then the story becomes more complicated. the observables I can prove at this moment is that they need to be continuous and bounded together with all of these derivatives. Otherwise, some special initial condition of the initial, the wave function needs to be taken care of, where I can hopefully use the initial condition as a modifier, but it will make my analysis much more complicated.
So I'm just going to be very naive here.
Sure.
So what do you mean by observable?
O is observable, which in our case can be, say, a polynomial of positions, polynomial of momentum, and anything you'd like, which in this particular discussion.
Like observable is some Hermitian operator.
Yeah, that's right.
But yours is one that depends on time.
No. The Hermitian, the observable do not depend on time. But as the dynamics is evolving in time, you look at the Heisenberg picture, then what you will get is precisely the initial observable that you begin with and sandwiched by, conjugated by the dynamics that you have. This is a Heisenberg.
So then, sorry, what does simple class mean?
Oh, simple class is what I just discussed. Is that okay? You have a function. If you have a function that is a phase function, that is a function of position and momentum, and then you take the quantization of that, and then now the question is, I need what types of this simple phase function that I can prove a bounds for. Well, this is just limitation of what the kind of bounds that I can prove. What I can prove is your function is C infinity on a torus, or your function is continuous together, is bounded together with all of its derivative on Rd. Otherwise, I cannot prove a bound of this. This was numerically still work, but this is a kind of the technicality that I have on.
I'm just being really stupid. So O is a Hermitian operator now on some infinite dimensional Hilbert space.
Yeah, that's right.
And that infinite dimensional Hilbert space you're interpreting as a space of functions.
Yeah.
And so that's what.
Yeah. O is the quantization of the phase space function.
Yeah,
and
that's
through the regular quantization procedure.
I'm back on board. Thanks.
Yeah. So if you put our estimate into place compared to the existing quantum algorithm estimate, and this is what you will see. This the Kerr complexity for Trotter is really just the number of Trotter steps. You can see that we get rid of this this H inverse completely, versus even in the vector norm you still have a H inverse. This is just putting in place so that you can imagine if you implement it quantumly using quantum circuits, the total gate complexity is polylog in terms of H inverse. I would assume this is optimal that we can do, but I do not have a theoretical lower bound showing that quantumly this is the optimal that I can do. And now I'm just going to go into, given the time limitation, I do want to get to my second part. Maybe let me just talk a little bit about the proving ideas of how I was able to prove these bounds. So conventional approaches typically in multi-scale problem, as what Steve was trying to illustrate, is you want to capture this mean, the multi-scale features. So what people typically do is this: you have a Trotter scheme. This is what you want to do, and there is a small parameter. What about taking the small parameter goes to 0, and if there is a very well-defined limit, well, although if there is a well-defined limit in terms of this procedure, you may not necessarily know the convergence rate can be exponential, can be polynomial, can be logarithmic. That's what you need to estimate. But suppose there is really a limit, you do the same thing for the Trotter, and it turns out you look at these limiting equations, and these limiting equations no longer have this small parameter h bar. That is the whole point that we want to get rid of. So hopefully you can get an estimate here, and then you just simply do a triangle inequality, so you will no longer get to this very boundary h bar, because this is a positive powers if you were able to prove that. So precisely when everything is spatially continuous, and well, this is using sort of a different setting, but the first work was really here, and when everything is all of this work assume that spatial. You do not need to have, you cannot have spatial initial discretization. When everything spatial is continuous, you can really make this sort of naive idea work. And however, the difficulty in terms of spatial discretization is not actually just as simple as I discretize, I think about the discretization error. The issue is because if you want to play around with this limiting procedure, the convergence in time is a strong convergence. However, in space is a weak star convergence. In other words, if you discretize it it on this level, you don't have, it's not clear what are the limits. It may very well do not exist. You lost of this very nice picture on the right-hand side, pretty much stating that you will start with here. That's where people get H inverse on the right-hand side. What can you do? So that is precisely what we do. Another thing I think is interesting to mention, even if you have spatial discretization and you still have this picture, but still if you think about it, by triangle inequality, you will always only be able to get an additive error bound. You will never get rid of the H inverse on the right-hand side. It will never be independent of H. The best you can do is additive. Let's just try to illustrate why this is actually not very natural, because you are just trying to do a trotter. As you take the trotter step L to infinity, well, it should be exact. This should be, you are exactly simulating what the dynamics is going on. You shouldn't be paying any sort of the error on the right-hand side. However, this type of estimate suggests you are still playing an error, which is really an artifact of this type of error estimate. It's not an artifact of what is going on in trotter by itself. So we would like to look at this problem, particularly in spatial discretization. You do not have these nice feature to utilize. Plus, I want to get a uniform on the right-hand side bound. I don't want to have an additive right-hand side bound. So I will not go into the details, but the point is that I just looking at precisely what I want to estimate. There is an easy way I can write exact error formulas. There's no expansion, no truncation, exact error formula. That is I can do. And then still you don't keep taking care of this spatial discretization, which is really the main difficulty here. So what the key observation of our work here is really that it turns out the spatially discretized operators can be identified as pseudo-differential operators on a quantized torus. This allows us to utilize the PDE tools, these continuous variable, the position, momentum operator, so on and so forth, to prove bounds for discrete problem. This is really the key contribution of our work, is to draw the link between discrete and the continuous. Just to say a little bit more, if you lost on this, I try to minimize the technicality, but if you do feel this slide is too much, after this slide, I will move on to another task. So it's time to come up if you will. So the Weil quantization, which is really just this op operator, which turns a space function into operators in the natural quantized form. This really agrees with our regular physical quantizations, which just says that you just treat it as a hat. This is a positional operator. This is a momentum operator. So this continuous operator is really nice to work with because, for example, if we take a look at of the commutator, I can easily calculate them. More generally, if I have a function A that is a function, phase space function of position and momentum, and so on and so forth, you no longer can calculate it explicitly by hand, but still semi-classical analysis and micro-local analysis tell you there is this very nice estimates, asymptotic you can write out exactly what is the remainder, these bounds that you can utilize and make things simple. So what I want to say is that these continuous things is really simple to work with. However, it doesn't address our problem because what I want to work with is the discrete problems. So this is just a simple illustration of what turns out the observation is that if you discretize this problem of using your choice of discretization, and it can be identified as a pseudo-differential operator of a different function. Recall this was p squared. This is a different function. It can be identified as a different function on a quantized torus. However, this, we are getting here, the really missing link is it would be so nice if there is a theorem joining between these two connections, so I can use these very easy to work with object to prove the discrete bounds. That's precisely what we can establish is that if I have a operator A, this is a C infinity. That's why I restrict our operators. The observable needs to be C infinity on a torus is because of these technical assumptions. And then it turns out these discrete norms can be upper bounded by its operator lifted norm from L2 to L2. This allows us to use the PDE tools for these discrete problems. So these are just some mathematical analysis, and the point is the whole thing works. You are welcome to check our paper. And this is just some ideas, and this is sort of a numerical illustration, and it just states that for the position momentum observables, if you shrink h and you keep the number of trotter steps the same, you shrink h, the error remains steady. However, you see that in the unitaries or in the solutions, the error actually grows. This was So the open question for this part is, first of all, can you prove a rigorous quantum bound saying that polylog gate complexity is the best you can do? Second is, of course, I want to treat the whole electron nuclei fully coupled problems. Before quantum computer, people do not want to do that entirely. But if what we are trying to say is suggesting that if you account the nuclei into this full molecular dynamic problem, the price you pay is minor. So but I don't have a proof yet. That's in work in progress. So now I'm going to move on to the second part.
11 minutes left, just to...
Oh, that's okay. That's really bad. Okay, so the second part of my talk is I'm going to discuss this problem of Hamiltonian learning. I'm very fortunate to work with this set of collaborators, and let me just go fast. So Hamiltonian learning belongs to this broader class of problem that is Hamiltonian learning, which means that you want to learn from quantum experiments. This is my definition of Hamiltonian learning. So the setup is typically, say, you have your unknown quantum system that is evolving in time. It can be on trusted quantum device, on trusted quantum computer, or maybe your lab laboratory experiments. And you have a quantum system that is evolving in time. The point is that there is some unknown part. You want to play around with some controlled operations to this unknown quantum system, prepare hopefully a product state, and then perform some measurements. You gather all of these data. You want to learn something about the underlying quantum system. There are various different things one can learn, but concisely what I'm going to talk about is this Hamiltonian learning problem. You can really think about this as the inverse problem of Hamiltonian simulation. The setup is I'm giving this dynamics, I want to learn the Hamiltonian out. So on a concrete level, what do we mean? We mean that I'm going to look at, now finally you see some tensors. I apologize for the first part, you don't see tensor. I have n-body Hamiltonians, and we know that n-body Hamiltonian can be written as linear combination of n-body polys. And then to learn the Hamiltonian out, we'll translate into learn each of these coefficients, let's say with a certain procedure epsilon. You can imagine this is certainly not an easy task because of the Hilbert space dimension. However, this is very important problems in quantum metrology and quantum sensing, as well as quantum information in general. People have been working on this. This is not up to date list, but people have been working on this problem for decades and years and many times. So typically for learning a many-body Hamiltonian problem, there are typically two metrics people or complexity people want to discuss. Number one is how many experiments you need. And number two is that each of the experiments you run the time you run the Hamiltonian for some time, you add them all together. This gives you the notion of total evolution time. Please, Sven.
Are you assuming the family of Hamiltonians you're looking at includes the ground truth, or not? Do you have that knowledge?
Ground truth? What do you mean?
Yeah. Does the family of Hamiltonians you're looking at?
Yeah.
To optimize, does it include the target Hamiltonian, or you don't know about that?
So I have a unknown Hamiltonian. I will show you. For example, I'm given a H that is a k-local Hamiltonian, and the task is I want to learn all of its coefficients.
Okay, so you have the right class of Hamiltonians.
Yeah, that's right. Otherwise, you cannot. Well, I will show later that our bounds is independent of the system size. Otherwise, you will have system size dependence, unfortunately. Yeah, very good question. So this is typically in the physical literature just called the standard quantum limit. For time consideration, I will not discuss precisely like what is a high-level idea behind these algorithms. But the takeaway is at best you have quadratic dependence on both of these metrics. Well, a very natural question as a theorist we ask ourselves all the time is, you have something, you have some bound, is it optimal? Can you prove this is optimal, or can you improve it further? So it turns out if you think it carefully, actually the quadratic is actually not necessarily the optimal. For example, if you think of simple body, forget about the many-body problem. Suppose on top of that you are just with one poly. There's only one parameter that you don't know, and it's associated with a poly Z. And then we do know that the total evolution time can be vastly cut down from quadratic to linear dependence. This in the literature is called the Heisenberg limit, and there are various different ways to approach it. This is not a complete list, but can be divided into two approaches. Either you prepare a highly entangled state to begin with, say JHC state, or you look at a longer evolution time and plus some phase estimations. I will not discuss these in detail, but you will see our work more aligned with the second one. But the point of these, so far is a state of art, but the point of the open question that was open in this community was really that people try to ask, can I really achieve the Heisenberg limit when I learn a many-body Hamiltonian? This is really a simple one-body Hamiltonian where you can achieve, but for many-body, can you really achieve the Heisenberg limit as well? And that is precisely what we are going to deal with. And ideally, even more, you can imagine, suppose you are in an ideal world, you try to come up with a wish list of your Hamiltonian learning algorithm or experimental protocol. Ideally, an algorithm you would like to have is basically the following. You would like the total evolution time to be Heisenberg limit. You would like the number of experiments as few as possible, definitely better, hopefully better than quadratic. The number of gates you need, hopefully you really want it to be as simple as possible. For example, we would prefer single qubit gates as opposed to multi-qubit gates. You would prefer Clifford gates as opposed to non-Clifford gates, and also as few as possible. Together, we certainly want some robustness regarding, say, the state preparation and the measurement error. If there is some error, hopefully you can still give me something. You're not giving me totally garbage. This is called the spam robust error. So, and when you have, say, some local Hamiltonian, say, geometric local Hamiltonian, which was assumed in the quadratic dependence papers usually, and we hope that all of these things can be made system size independent. Yeah, thank you. And I can show you the result, and I think that's pretty much it. And I don't show you how I prove it, but that's good, I think. So the answer for in our work is yes, we indeed can do that. We propose the first learning protocol precisely to achieve a learning many-body Hamiltonian in the Heisenberg limit. More on concrete level, what do? We have this so-called low intersection Hamiltonian, which is a generalization of geometric local Hamiltonians. So any geometric local Hamiltonian in any fixed dimension, you can show its low intersection. And we have total evolution time that is Heisenberg limit. We also prove a matched lower bound. And the second is number of experiments we can get away with polylog as approach to linear, as approach to quadratic. You can call it a super polynomial or exponential improvements if you'd like. The number of layers of gates is also system independent. And it turns out we only need single qubit Clifford gates, which is the best you can hope for. And on top of that, we do have spam robust. So pretty much we fulfill all of the things that one could hope for. So just I don't think I will have time to tell you precisely how we prove this. But just
how can you get a time 1 over epsilon with a number of gates 1 over epsilon to the 1.5?
Oh, you mean this? Oh, no. This means this is a total evolution time, which means how long you run your experiments, your unknown Hamiltonian, which has a t. You add all of these time.
Oh, sorry,
yeah,
that's a
unknown Hamiltonian. Yeah. This is yeah. Thank you for the question. And just say a little bit more how you should understand our results. So first of all, what is this mysterious low intersection Hamiltonian? It's actually not mysterious. This is precisely the definition. In the literature, it's also called a bounded degree Hamiltonian. Just to say that any geometric local Hamiltonian, any fixed dimension, take your favorite model, they are all belongs to low intersection. It's a slightly more generalized class than what people typically look at. And the second thing is about error metric. So in our algorithm, in our theorem, the error metric we choose is the probability, the failure is basically the success probability, which is a confidence interval error metric. Well, you might think that, well, then I have this failure probability, which is delta. How does failure probability place in the role of my, my whole theorem? It turns out the failure probability only comes in logarithmic fashion, and our lower bounds also prove that it's linear in epsilon and log in so we account both of these in terms of our lower bound results. So it matches, which means that this is optimal that one can do well. So another thing is that this really states that I only, suppose I get arbitrary one parameters that you want to estimate, and this is what you have. You may wonder, what about I want to get all of the parameters? And then it just follows by a simple union bound argument. You will see that you replace this delta inverse in the log by n times delta inverse. You pay a log of n cost, which is sort of not substantial. And in quantum metrology, and I also want to address a little bit, people typically not necessarily look at the confidence interval error metric. Instead of people like to look at the standard deviation. Well, what I just want to say is that mathematically speaking, in most of the cases, confidence interval is contains more information in the sense that confidence interval typically can give you a good bound of standard deviation, but not necessarily vice versa. Just to say there is a simple calculation which shows that you can get this standard deviation in the Heisenberg limit, almost Heisenberg limit, epsilon, instead of this epsilon, you can get epsilon log epsilon. However, we have a refined analysis showing that the log factor is completely not necessary, just to show why we choose this particular error metric. And I think I should not have time to discuss maybe just one little technique before I end.
You can try to see the question. Maybe someone asks for something later.
Yeah. So the technique that we use is really you have this unknown Hamiltonian, and it's a many-body Hamiltonian, maybe highly entangled. And but the thing is that if you insert some polys somewhere, because polys are both Hermitian and unitary, you can really conjugate a poly. What this reshaping technique essentially is doing is that it's intrinsically changing what is the underlying physics dynamics that you are having. I'm not open the black box by applying some polys, the dynamics changes. You may wonder, can I do different polys? Of course. Can you do linear combination of polys? The answer is certainly yes. How? This is precise the product formulas that I have discussed earlier. So all of these error estimates results will rely on a robust system size independent error estimate for the product formulas, for examples. But I will not have time to show you that. Let me just, if you're interested, I can go into more details with you afterwards. Just to say that here is an overall illustration of our protocol. We insert a bunch of polys and we reshape the system into a way that is easier to calculate. And there are, say, a bunch of detached smaller systems so that you can make one measurement, get a lot of information at once. That's essentially how we were able to cut down the cost. And this gives you a reshaped Hamiltonian, and then you perform the phase estimation. And there is some error estimates, but here is our theorem, which states that, okay, total evolution time is what I presented, and we also have a matched lower bound. So later, people have been trying to ask that, is this a form of control where I need to insert some of the poly? This is a form of control of your quantum system. Is that necessary? Do you have to be able to control your quantum system in a certain way in order to achieve Heisenberg limit? This is a very nice result last year by these folks. They show that quantum control is actually necessary, some form. Otherwise, you cannot achieve Heisenberg limit. I recommend you to take a look of this. So I think I can summarize. This is the paper. This two is the two paper I mainly emphasized. The other two I just mentioned, but I didn't go into. And if you're interested, I didn't have time to finish the Hamiltonian learning part, but if you're interested, I invite you to look at Huang's talk at QIP and also Tong's talk at IPAM. In particular, Tong's talk also revisited gave a survey of all different works in Hamiltonian simulations recently. So if you are interested, you are welcome to look at that. With that, thank you for your attention.